Section 5.5 of your text is on early gambling experiments. A lot of the initial study of probability came from studying gambling. If there's anything to motivate people to study and learn new things, it's making money. And if, think about it, either if you're gambling or if you are running a casino, it's really important that you understand the probability of every possible outcome of a certain game. So that you can, calculate the way to make the most money or take the most money away from people. We're going to get further into how casinos are set up so that they always make a profit in the next section. But this section, we're going to talk about, how they initially started to discover some things. So we'll start with this example. Here we're being told a fair coin is tossed 4 times. Bets are taken on how many heads will turn up. We're first asked to list all equally likely outcomes. Then we're asked to construct a histogram for how many times we would expect 0, 1, 2, 3, and 4 heads to occur. Then we're asked to find the probability for 2 heads turning up. And then we're asked how betting on 2 heads turning up will do in the long run. So back to part A, where they want us to list all equally likely outcomes. Before we try and write the sample space for this, we want to consider, what could possibly happen. And B kinds of gives us a little bit of a clue to that, right? If we have 4 coins that we're tossing, we can end up with all tails, so that would be 0 heads. We could end up with 4 heads on all coins, which would be 4 heads, or we could end up with anything in between that, 1, 2, or 3. So these are the only possible numbers of heads that could turn up, and this is going to help us, list our sample space. So we'll start this off by taking into account the number of heads that can show up. Okay, and we're doing this just to keep our sample space a little bit more organized. So we could end up with 0 heads, right? And the only way that could happen is if we get all 4 tails. We could end up with 1 head, and there's a few ways that that could happen. So we could, we're just going to alternate where we place the head over here. It's supposed to be a tail. Okay, that's all of the ways we could end up with 1 head. Then we could also end up with 2 heads and 2 tails, and there's some more possibilities for this, right? We could end up with head, head, tail, tail. Tail, tail, head, head. Tail, head, head, tail. Head, tail, tail, head. We have head, tail, head, tail. And tail, head, tail, head. Okay, so those are all of the possibilities for that. Then for 3 heads, now all we need to do is go back in the situation where we only have 1 head and change all of the tails to heads and all of the heads to tails. So that's every way we can end up with 3 heads. And then for 4 heads, the only way that can happen is if we end up landing on all 4 heads. Okay, so everything that we have over here, these are all of our equally likely possible outcomes. And it turns out there's 16 of them. Okay, so these are all of our equally likely, and there's 16 of them. Okay, we have 16 equally likely possible outcomes. So now let's go back to the question we had here. So part A was just asking us to list all of them. So that's everything in here. Now part B is asking us to construct a histogram for how many times we would expect 0, 1, 2, 3, and 4 heads to occur. Okay. So we're going to use the information that we have over here in order to do that. Correct. Now, in order to construct a histogram from this information, what we're going to do is treat this like it's data, and we're going to group it into classes. Right, so we're going to take into account the number of heads we have as the different classes we're working with. And we're going to consider everything here in our sample space to be like our data. So number of heads are like our classes, and then tally is going to be how many times each thing shows up. So there was 1 way, to get 1 head. There were 4 ways to get 1 head. 1 way to get 0 heads, 4 ways to get 1 head. 6 ways get 6 ways to get 2 heads, 4 ways to get 3 heads, and then 1 way to get 4 heads. Then we're going to take into account what the probability is of each possibility. So the probability of getting 0 heads is going to be 1 out of 16, right? Because we have 16 things here total. Then 4 out of 16 is going to be our probability of getting 1 head. 6 out of 16 is our probability of getting 2 heads. Then 4 out of 16 again, and then 1 out of 16. If we convert all of these to decimals, we end up with 0.0625 or 6.25%. We end up with 0.25 or 25%, 0.375 or 37.5%, and then this is going to give us 25% again and 6.25% again. Okay, now we're going to continue using this information to actually construct our histogram. This is what's going to go on our x-axis, the number of heads, and the probabilities that we have is going to go on our y-axis. Right? The way the question was originally worded is construct a histogram for how many times we would expect 0, 1, 2, 3, and 4 heads to show up. So we'll go with the probabilities that they gave us. Right? This could also be called a probability histogram. And I think you'll see that term referred to in this chapter in your textbook. Okay, so number of heads is going to go on our x-axis. And let's see, and we want to now put probability on our y-axis. And we want to give this a title, so I don't know, we'll call it like tossing 4 coins or something like that. The heights of the bars we're going to base off of the information that we found over here. Okay, so it's going to be easiest to do this by making our y-axis based on 16ths. So that's what we'll do here. Right, so let's see, we have 1, 2, 3, 4, 5, 6, 7. Right, where each line is going to denote 1/16, right? So this would be 1/16, actually this would be 3/16, 5/16, 7/16. Let's see, this might be a little bit clearer. This should be 6 out of 16, this will be 4 out of 16, and this will be 2 out of 16. Okay, so for 0, we have probability is 1 out of 16 that we're going to get 0 heads. So if we draw our bar going up to here, going up to 1 out of 16, that's our bar for 0. Now our bar for 1, the probability of getting 1 head is 4 out of 16. So we'll go up to 4/16 over here. We'll draw a bar for 1. Our probability of getting 2 out of 16 was 6 out of 16. I mean, our probability for getting 2 heads out of 4 coin flips was 6 out of 16. And then, yeah, our probability of 3 heads was 4/16 again, and our probability of 4 heads was 1/16 again. Right, so just to make this a little bit easier to read, I'm going to write the probabilities on top of the bars. Okay, so this is the histogram that we have. And this would be an example of a probability distribution, which is something we'll talk about more in the next section. Now back to part C. They wanted us to find the probability of there being 2 heads. If we go back to the information that we had before, we found it here. The probability of there being 2 heads was 6 out of 16. That's our solution to part C. For 6 out of 16, or 37.5%. Okay, now we'll get back to part D. Part D is asking, how will betting on 2 heads do in the long run? So based on the information that we have here, what this means is if we keep, when they say betting in the long run, what they mean is suppose you had an infinite amount of money and you just kept betting on two heads every single time you gambled. How many times would you expect to win and how many times would you expect to lose? We can see from the histogram we made and also from the probabilities that we calculated that two heads is the most likely thing to happen, at 37.5%. But when we talk about what does it mean in the long run, they want to know, well, on average, how many times could you expect to be winning versus how many times could you expect to be losing? Here, if we're winning 6 times or 6 out of 16 times on average, that means we're losing 10 out of 16 times on average. Right? So in the long run, so if you keep playing again and again, your ratio of wins to losses would probably be about 6 to 10. Right? So you'd be winning 6 out of 16 times, you would be losing about 10 out of 16 times. So another way we could word that is we could say, right, so the win-lose ratio should be 6 to 10. Now, what's interesting about this problem is in this example, we just did this for flipping one coin, or for flipping 4 coins, or for flipping 1 coin 4 times. If we go back and look at the shape of this histogram here, right, this is something that's roughly bell-shaped. So, we can kind of, if we were to kind of connect the tops of these bars, we would end up with a shape like this that's roughly bell-shaped. If we increase the amount of coins that we're flipping, this is going to look less and less like a histogram, and it's going to look more and more like a curve as we do this with more and more coins. And this is the shape of the normal curve that we're going to be seeing in Chapter 6. So these are examples in your book of what it would look like if 12 coins were flipped and we wanted to find the probability of getting 0, 1, 2, 3 all the way up to 12 heads. And then this is another histogram for the probabilities of getting, 0 through 50 heads if we were to flip 50 coins. So as you can see, right, like over here, we're starting to see something of a normal curve emerge. It's looking more and more like a curve as there are more and more bars added in as we flip more and more coins. We can also see this type of shape emerge in histograms if we do other probability examples. They don't always just have to be about, flipping coins and seeing how many heads come up. In this example, we'll see what happens when we roll 2 dice. We want to find the probability of obtaining sums 2, 3, 4, all the way up to 12. And then we want to construct a probability histogram. Okay, so we'll take a look at the sample space we've seen before for rolling 2 dice. And, again, we've seen how we can see, the sums when we roll the 2 dice. 1 and 1 is 2, 1 and 2, 2 and 1 are 3, and so on along all of these diagonals if we've generated our sample space like this. So now we can use this to figure out what the probabilities are of getting all of these sums 2 through 7. So we can write out what our sum is, 8, and then a probability. Right, so if we want to look at 2, there's only one way we can possibly get a sum of 2, so the probability is going to be 1 out of 36. And again, just remember, there's 36 possibilities here. Probability of getting a sum of 3 is going to be 2 out of 36. And I'm just going to follow through the other ones like this, where we have 3 things that'll give us a sum of 4. We have 4 possibilities that'll give us a sum of 5. 5 possibilities that'll give us a sum of 6. 6 possibilities that'll give us a sum of 7, and so on. So these are all things that could possibly happen. And this is the information that we're going to use when we construct our probability histogram. Okay, our y-axis is going to be probability. And our x-axis is going to be the sum on the dice. Right, so we'll start with, 1. Obviously, that's not possible. And then our probabilities, we can mark this y-axis being, 1/36 is what we'll count up by. And we'll title it, something relevant, like someone we're rolling 2 dice. Okay, so now we'll start drawing our bars, and we're going to get the heights of the bars based on, the probabilities that we found over here from looking at our sample space. Right, so again, probability of getting a sum of 2 is 1/36. So that tells us what the height of that bar is. Sum of the next one, or probability of the next one, 2/36. And then we'll just keep going and following along with the chart that we have. 4, 5, 6, 7. Okay. And then this is the histogram that we have here. And again, we can kind of see, it follows the same type of curve shape that the other problem did. It's not exactly the same, but it still has that same general shape. And we can mark the tops of these bars with the probabilities just so that, it's a little bit easier to read.